Okay, Aaron, please start.
Okay, hi. So today's paper is about the cause and effects of fitness landscapes in unit test generation. So just a quick overview of what this paper is about. Okay, so genetic algorithms have proven to be effective in generating tests that achieve high code or branch coverage, but it's still far from being able to satisfy all the test goals, which is basically cover all branches. So one example of the problem is generating complex parameter objects. And another reason is because we have a lack of understanding of the search behavior during the optimization process. And it is hard to identify the factors that make a search problem difficult. So what this paper tries to do is understand by investigating the underlying structure of the search space, which is the fitness landscape. So by analyzing the fitness landscape, we can investigate the impact of its properties on the software search test. So just a quick background on search-based software testing. Basically, it applies meta-heuristic optimization techniques to generate test data. And the most common optimization goal is branch coverage. So genetic algorithms is more common for unit testing. So how it works is, firstly, it populates a generation of random individuals, and then we calculate the fitness value for each individual. And for the next generation, we will use a fitter individual to cross over or mutate to build the next generation. And the most common fitness function that we'll look at is the approach level plus branch distance. So for the fitness landscape analysis, basically the fitness landscape is the underlying topological structure of the search space, which is basically the fitness graph. So to define it formally, the fitness landscape is consists of S, F, and N of a problem instance for a given optimization problem. So S is just a set of the genotypes or the chromosomes. F is the fitness function, and N is the genetic operator. So fitness landscapes are usually defined by these two main features, ruggedness and neutrality. So we'll go through both of the features. For ruggedness, this is an example of the fitness graph. Okay, so basically there is multiple local optima and there's an isolated global optimum. So one worry is that for rugged landscapes, we worry that the algorithm might get trapped in the local optima and result in like suboptimal solutions. And one way to analyze this type of landscapes is by using a landscape walk called the random walk. So basically, you just randomly initialize an individual, and then we move to neighboring individuals in each step using the genetic operator, which is basically just crossover or mutate the individual. So we just keep repeating that and get the fitness value for each mutated individual. So this is useful because we can use these fitness values to evaluate to get like some fitness landscape analysis matrix, which we will go through later. And the next feature is basically the opposite of ruggedness, which is neutrality. And basically it means where it means that the landscape has a lot of the tools. So the neighboring values are mostly equal to each other. And it can be analyzed using a neutral walk, just a variation of random walk. And basically, it accepts neighbors with identical fitness values. But for this paper, we'll just be doing the random walk.
Hmm.
Yeah. So from the random walk, we will get a sequence of fitness values, and then we need some measurements, some metrics to analyze these fitness values. And using this matrix, we can measure both the ruggedness and the neutrality of a fitness landscape. So
So
this is the first measurement, which
here
is
they propose a very general concept called the ruggedness and the neutrality. So the flat problems or the flat effect we're going to address can fall into the problem of neutrality. So maybe I raised these questions earlier, a little bit earlier. So this paper is more like to propose the concept of the ruggedness and the neutralities, and have no one proposed before, but people are actually aware of it. So is there any follow-up solutions to address both ruggedness and the neutrality? Is this paper mentioned that there are solutions?
It suggests some solutions, but it doesn't go in depth into them. So
Okay.
what this paper wants to do is just analyze how this ruggedness and neutrality translates to the source code.
And also it provides some, it at least provides some examples, right? I mean, so
The example,
did it provide some examples for ruggedness and neutrality?
so they didn't provide any like source code examples.
Okay, they do not have source code examples. Okay, please go on.
Just mention
So
them. Yeah.
yeah, I can understand. I feel that the majority of people, majority of students here may not wear the story part. So I think it's very easy for us to raise examples for neutrality. But for ruggedness, so Aaron, suppose I'm raising questions, you may not necessarily answer it now. But if you're going to construct a possible a rugged test case, is that probably is that for us to quickly come up again? Is that possible for us to quickly come up with examples for such a ruggedness?
As in like using this paper.
Yeah. So raising examples, so somehow, I think one of the ruggedness is more like this. Suppose this example is x equals to y, right? And the next branch is x should be greater than 10k. And we need, so here's the bug. Suppose here's the bug. So we would like to generate an x and a y so that it can satisfy these two conditions, right? So suppose we are using search-based test case. It might be very easy for us to generate a test case like 0 and 0, right? And based on the fitness, and giving the fitness of this function is supposed to be x minus 10k. This is a branch distance, right? But actually, it still need to be normalized into some 0 and 1. Then we'll add a push level. So the push level is supposed to be, let me write in a push level here. A push level here. So giving these fitness functions, suppose because giving the fitness functions, the one who passing x and y will have a higher, will have a smaller approach level. So suppose let x equals 0, y equals 0, and this branch distance is supposed to be 0 because this condition is satisfied, and the normalized 10k, and it is supposed to be 0.999, etc. Right? suppose the normalized function x equals 1 plus x, x over 1 plus x. Suppose this is normalized wave function. So this is the first case. However, if we would like to, based on this, evolving from these solutions into a solution satisfying both conditions, then the problem lies in it as long as we change the x, because these conditions is only relevant to x. So as long as we change maybe 0 to 1000, right? If we change x from 0 to 1000, it makes the solutions closer to satisfying these conditions. However, the first condition will never satisfy. So in this case, the problem becomes 1, right? So our approach level becomes 1, and the plus, because this 1001, so it will normalize to 1000. It will become 1.99, etc. So more like giving these conditions, it's more like a ruggedness. So the idea is that there's a way. Suppose there's a local optimal here, and we can start with the solutions. Maybe we can go down from the first step. However, the next step, it will go through a huge number of local optimal, and finally we can reach the local optimal. So giving these specific functions, that landscape is called the ruggedness. Right. So I hope that I can explain. I think Aaron may understand it. For other students, may not necessarily take the point. Okay, please go on.
So now we'll introduce 6 different measures. So the first one is called autocorrelation. Basically it's a correlation function. So it measures the correlation between the fitness of 2 individuals s steps away. So basically if this AC value is close to 0, it means that the individuals are less correlated. So it means that the fitness landscape is more rugged. So the AC value is close to 0.
So here is going to change. This is the F means the fitness of 2 individuals.
F is the fitness of the I individual.
Okay. So it's more like so start with F0 until it goes through a few F into Fs, right? So it's going to compare Fi to Fs. So what does this big N mean? This is N, right? This is N.
Yeah.
So
N is the number of.
Is that keep evolving F0 to Fn?
Yes.
So you start. So what is F bar? F bar is the average, is the mean number of the fitness. So it actually compare. Okay. So it's more like a compare the variation.
Yeah, I'm not very sure.
What does this what does this S mean? And S is the determinant. It is the parameters here.
Yeah. So they didn't mention like what value they use as. Yeah.
Individuals less correlated. So autocorrelated. I somehow measure the correlation between the fitness 2 individuals S steps away. And S stepped away. Okay. So suppose this one is a S. And how does the N means? Fi means finish about individual affirming. So can you somehow explain these equations? This is more like the difference between each fitness, the difference between each fitness and the average. And so we sum up them together. And this S, how does this S determine? So what does this N minus S means?
Yeah, because you are because the N, the last number will be N minus S because of the second bracket. There's a F I plus S. So basically you just compare the two individuals, they are like S steps away. Then
so this is actually
from there
so this is N and this is S. So each interval is an S, right?
Yeah.
Interval is S. So suppose so this is a multiplication. This is times. More rapid when AC value is close to 0. So let's raise an example. Suppose this value looks like this. This is F1 and F2, 3, 4, 5, 6. Suppose this 6 value and let S equal to 3, right? So in this case, the whole variation, and this is the area number, suppose 0, minus 1, 1, so it was supposed to be 6, right? The whole number is 6. And let S be 3. Let the step to be 3. So, okay, so that means the variations. So it means the shape is more like from, and if I understand correctly, that means giving an individual F, giving individual I, it make unconsecutive mutations on I. So make one mutations, I1 changing to I2, and the second mutations, I2 change to I3. And based on these mutations, we will have IN, right?
Yeah.
So this is a sequence of mutations. And so we will have interval of S. So the idea is that we're going to see the perturbations because so this matrix or this component or the denominator actually evaluate the perturbation, the value or amount or the quantity of the perturbations of all these sequence. So the finite values may look like this one. And for this part, is going to check how suppose let S becomes N. Let S becomes N. And so it will be, so this one will be only be one value, right? Suppose S equals 1 minus 1. So this would be one value. So the denominator will be F1 minus F plus Fn. I supposed to be 1 and S minus 1 N minus F bar, right? And they supposed to be the same. And how these, if I'm to evaluate this finish, I may come up with different equations, perturbations. Amount. And what if it is monotonic? What if the landscape is monotonic? So each one might still be the same. Among recent questions, what if the landscape is monotonic, like this landscape? Will it still be zero?
No, it should be closer to 1.
Closer to 1. Why? Okay, so there's a sign, right? There's a sign. So this one will be very large. So the idea is that suppose this is the perturbation, so it's likely that the value I and I plus s will be in different sign. So it was supposed to be negative value. Okay, this value can be negative value, right?
Yeah.
Can be negative value. So okay, the point is that the smaller it is, the more likely to be wrecked. Otherwise, otherwise fi and fsi. Okay, the point is that the sign here. The point is the sign is the sign here. Suppose it is monotonic or it's more neutral, and fi plus s are more likely both larger or smaller than the average number. So if they're both the sign, so it will be becomes the FRS supposed to be larger, right?
Yeah.
If it is larger, then it will be close to this value. Okay, I somehow get the point. What's going on?
So the second measure is neutrality distance. So it's basically the number of neutral steps made from the start of the random walk. So for random walk x1 to xn, nd is the largest t such that the fitness value of x1 equals to x2 equals to all the way until xt.
So it choose the largest number where the largest, it counts the quantity of the individual share the same fitness.
Yeah, but it's only from the start of the walk. So higher T will mean that.
So do the authors have some empirical study to see that what is the phenomenon? Suppose they have two, they have the phenomenon. Suppose they have the landscape. Suppose they have the empirical study, right? The empirical study. So this is the neutral, it is from neutralities, and this is from the this is from the ruggedness. The number of neutralities, the number of ruggedness, and the next one is the nonism. So it was neither neutral nor rect. So they're supposed to have a quantity or the comparison of numbers of methods to suffer from distillation. Does the author have such a comparison on that part?
Yeah, so that's the empirical stuff.
Okay,
yeah.
Sure.
Yeah, so the third measure is neutrality volume. So try to find like the sets of individuals with equal fitness values. So for the first example, NV equals to 3 because there are 3 different sets, consecutive sets. Then
so I'm asking
for the second example, NV equals.
I'm asking that for these values, suppose it must be started with the Fi, right? So if this is Fi start with F2 and then mutate from F2 to F3, or we start F1 to mutate multiple F2, F3, F4. So the first one or the second one? It's going to find a
The first
neighbor,
one.
the first one. So it's consecutive mutate an individual.
Yeah.
So it's applying the mutations on the result of the previous mutation.
Yeah.
So it does not it does not just simply take the neighbors of the individual. Okay, please go on.
So it means that the first example is flatter. So if the MV is lower, it means that there are more fitness values that are equal.
Maybe you can also using entropy to calculate it, right? We can take the
So the
entropy.
next three ones, the next three ones are based on entropy. So basically it's based on information analysis. So it still depends on the sequence of fitness values, but we first apply the following steps on them. So the first step is basically we just change it into fitness changes. So for example, if the first block is the first set is the fitness values, we just minus the next value from the previous value to get the changes. And then the second step is to convert the changes into only these three possible numbers, 1 bar, 0, or 1. So it's 1 bar if the change is less than a certain threshold, E. So one example is using the same example from previously, with E equals to 0.05. We can change the we can modify the different fitness changes into these three symbols. So in the end, we'll just get a
So
string
this is more
of
like a -1, right? This is -1 or the simple one.
So in the end, you'll just get a string of these three symbols. So for the fourth measurement is, like you say, is the entropy measure, and it is a measure of the number of consecutive symbols that are not equal, which is PQ. So basically, PQ can be like -1, 0 or 0, 1, for example.
So why does it take a lot of 6?
They didn't mention that.
6 means that there is a 6 options. So one of the explanation might be it will only select it have six type of mutation. Okay.
So if the entropy increases, it means that there is a high number of symbols that are not equal, which means that there are a higher number of peaks. So the next one is partial information content. So the first step it does is it will filter the string, the original string into S prime by removing all the zeros. And then after that, any symbols equal to their preceding symbol will be removed also. So in the end, S prime will have to form of like 1 bar, 1, 1 bar, 1. So the measurement M is basically the difference, or rather the ratio between the two different lengths of strings. So if M equals to 1, it means that the string was not truncated at all. So the string did not have any zeros, which means that the landscape is maximally multimodal, which means there's a lot of peaks. And then if M is 0, it means that the truncated string has a length of 0, which means that the original string had all zeros. Which means that the landscape is just one long flat plateau. So for the last measurement is density basin information. So is like the opposite of the information content. Basically, instead of taking subblocks that are not equal, they take subblocks that have equal symbols. So either 0, 0, 1, 1 or 1 bar, 1 bar. So like the opposite of information content, if the H increases, it means that the number of peaks decreases. Yeah. So these are the 6 measurements that they'll use in the empirical studies. So firstly, just to go through the research questions. The first one is asking, what are the properties of the fitness landscape for the JUnit test generation problem? So whether the fitness landscape is neutral or rugged. And then the second question is based on the properties. How does it affect the search behavior? And lastly, we want to relate the source code with the different fitness landscapes.
Oh, let me see
So,
the last question. Underlying probably inference. Okay, please go on.
yeah. So the experiment setup, they use 331 Java classes with various complexity range. Then it uses Evo suite with MOSA algorithm. And what it does is it applies the random walk on each class and then apply all the 6 different measures on the sequence of fitness values obtained. So the target criteria is branch coverage, and the search budget is default 60 seconds. And they also use the most common number of random walk steps, which is 1000. So to account for the randomness of both the MOSA algorithm and the random walk, they repeated it for 30 times on each class. Yeah.
So they test on the class level, right? So they are going to generate a test case for a Java class instead of a Java method.
Yeah.
So do they using the test? Do they evolve on the test field or the test case?
Sorry, what do you mean?
So do they evolve on test case or test field? Because they under the MOSA algorithm, they're supposed to evolve on the test case chronogram instead of test field chronogram. The test field they evolve on test case.
Yeah.
Okay.
Yeah. So the first question is basically you want to find out the properties of the fitness landscape.
The problem is here. Why does it bother to use it? Why does it bother to use MOSA algorithm? So because the MOSA algorithm is just to maximize the branch coverage, right? But
yes.
but after all, for each branch, given that it's going to calculate the fitness, so the fitness is each branch giving the the MOSA algorithms, each branch will have a fitness function, will have a fitness, right? So giving and for each mutation, they will have different fitness. So giving the test case, given the test case, it will have different fitness for different branches. And how does it calculate it?
Yeah, so to calculate the fitness values, we use the random walk. But the MOSA algorithm
the random walk is that we randomly apply mutation operations on the original test case, right? But this test case can have multiple fitness, each corresponding to different branches. And if I'm the one who designed the experiment, So it's somehow we will select, so we may not use the multi-algorithms. We will actually randomly pick a class, and then we randomly pick a method, and then we randomly pick a branch in this method. So we're going to then generate a test case for this branch to see, because in that case, each test case only corresponding to one, it will only correspond to one branch. So it will have only one fitness. And for their experiment, they use MOSA. And again, MOSA, and also the MOSA is just evolved on the whole Java class. When it works on the whole Java class, it will suppose to have, just as you mentioned, it could have 1,000 branches. So each test case will have 1,000 fitness.
Yeah.
And how does it calculate this neutrality and ruggedness based on multiple fitness?
Also, we use a random walk to
yes,
get
the random walk is just we apply a random mutation on the original test, right? But each test will have multiple fitness.
No, it applies it on each branch.
Okay.
Yeah. Then the NUS algorithm is later to test on these branches to test how the search algorithm works.
Okay, so they still work on each. Okay, so so each branch will have multiple tests. So in this case, AC for each branch will have.
Yeah. So
this is for one test case, right? So it will evolve on one test case, but it will check the evaluations on multiple branch simultaneously.
Yep. Yeah, so the example is we have 5 branches, and then we just take 6 steps. But in the actual one, we have 1,000 steps. So in this example, we have 6 different fitness values for each branch. And then for these different sequences, we can generate the different landscape measures. So across all the branches, we will consider the distribution of the 6 different landscape measures. Yeah, so we do this to get the properties of the fitness landscape.
Okay. If we're using MOSA algorithms, we will always keep the best. We'll always keep the best. We will always keep the best test case, right?
Yeah, as in this one is just random walk.
Yeah, it will have random. This is the random walk. So if the researchers are going to do this experiment, somehow we should remove the selection part of the evolving algorithm. You can see when we have search-based algorithms, we will have a fitness value. We will evaluating how close a test is going to cover a branch. So that is fitness. The second part that we're going to apply a mutation on it. It can involve crossover and mutation. So I think majorly it's about mutations. And finally, after one evaluations, after evolving for one iterations, it will generate some offsprings. So each individual will have an offspring. So it must have a mechanism to select the most fit individual from both parents and offsprings for next round evolution, right?
Yeah.
So in this whole algorithm, if it claims to apply random walk, so it means that it does not have the component of selection.
So it doesn't select anything. It will just
That it's just going to apply random stuff. But if apply random walk, it will so it is very possible that it will look into the neutrality.
Sorry?
What I mean is that given a landscape, because for this landscape, the landscape could be very complicated. So the ruggedness and the neutrality. Suppose a landscape has so the landscape could be both neutral and rugged and monotonic. Is that possible? Suppose there's a 3D space. Suppose there's 3D space here, right? And the space could be like this. We have a plateau here, and this part is monotonic, and this part is very rugged. Supposing in 2D space, more like this, right? In this case, and how do we? But such a landscape, it is different from different space. It actually differ from it, and also the landscape could be very large. I'm going to ask. So giving that if there's a search space like this, how do we classify this rugged or neutral or etc. And by the way, so let me confirm. So suppose the landscape looks like this. It is not rugged, right? Yeah. It will be close to 1. It will not be rugged. And also it's not neutral. So how does it only looking to the rugged and the neutral landscape? And does these researchers propose what kind of landscape is more friendly for search-based testing?
Yeah. Okay. So it's just the research question too. Yeah, but and
also, so here I come back to the question. Suppose this landscape, some part of the landscape is rugged, and some part of the landscape is neutral, and some part of the landscape is monotonic. And I think in this case, is that good to just using one matrix to describe the landscape? For example, suppose they have this landscape have 2 parts. The first part is totally plate, but as long as it's going to the another part, it will have a very good shape of the monotonic landscape. Very good. This landscape will be very good. So in this case, suppose we pick the point here, and also it looks into the moving, right? Suppose it is randomly picked up. This largely depends on how we initialize the test. Suppose we initialize the test case here, the landscape is supposed to be very good. But if we initialize the test being here, then the landscape will be very bad. And how does the authors to balance these 2 effects?
Yeah, they only categorize them as rugged or neutral. So they didn't take into account like a mixture.
Yeah, sometimes I just feel the landscape is very large, just like the neural network training. Suppose we have a good initialization, so the network can be trained in a very smooth way. But if we start at some point which is very difficult for the network to evolve, then it will be totally a different case. So I just feel that I just raised a question because Gordon Fraser used to be our collaborator. So in this case, I think it's good that for them to fully explore the potential landscape, they're using a single matrix to describe they're using single matrix, one matrix including ACs, including entropy, to describe the total landscape, of one branch. But in that case, I feel it is not, one single matrix may not be descriptive. So that is my feeling. And also, just based on this single matrix, it is not enough for us to provide enough guidance, or it's not informative for us to think about the potential solution, right? Okay, please keep going on.
Yeah, so from the distributions of the different matrices, like you see, this figure shows that the landscape is mostly dominated by the twos. So it's mostly neutral. So for example, most of the branches have a autocorrelation of more than 0.6, which means that the landscape is smooth because the thinness values are highly correlated.
Huh? If AC is large, correlated thinness, it means the landscape is smooth. Okay, yeah.
So
it's not
neutral.
necessary. Okay, it's neutral. So yeah, smooth does not mean monotonic, right? Smooth can be either monotonic or neutral.
Yeah. Then another one is, for example, the information content is close to 0.1. So the entropy of non-equal symbols are very low. So the landscape is also neutral. Yeah. So they also try to investigate the branches with, for example, if the branch have a small AC value, it also has a higher value for information content. So it shows that the rugged landscapes have opposite values. So yeah,
so the takeaway is that the whole landscape is very neutral.
Yeah, for most branches.
The branches wrapped the landscapes have the opposite value. Okay, so the higher values. What I somehow forgot what is the dBi. What is a dBi mean?
dBi is like the opposite of information content. So instead of getting the non-equal symbols, they get the equal symbols.
Okay,
so if there's a high
the more equals, the more equals, the higher the value here. Okay, please.
Yeah. So now I want to find out like how these thinness landscape properties affect a search behavior. So to do this, we need to measure the outcome of each individual branch. And to do so, we define a success rate. And it's basically the fraction of runs that MOSA will cover the branch. So for example, if we run MOSA 5 times and in only 2 times the branch is covered, then the success rate is 2/5. So this success rate depends on the random walk also, because for each run the random walk will be different because it's random. So we have to correlate the success rate with the AC measure also.
There is a selection. So if there's a set of, so if there's no selections, MOSA is just like a random testing.
No, so now they are running MOSA instead of the random walk.
Okay, I see.
Yeah. So they are running the search. Basically, you want to find out the behavior of this search algorithm based on the different landscape properties. Yeah. So This next figure, it shows the correlation of the success rate with the different measures. So the largest positive correlation is from information content. So basically, as mentioned, if there's a high information content value, it means that there's a large number of picks. So this goes well with the hypothesis
So
that
the basic idea is that the less neutral, as long as the landscape is neutral, is not neutral, there will be a hope.
Yeah, there will be a higher success rate. And another example is the largest negative correlation, which is the density basin information, which is the opposite of information content. So that's why it's a negative correlation instead. And the weakest correlation is the autocorrelation measure. So they only mentioned that basically measuring the correlation between the fitness values is not always helpful in predicting the problem difficulty. So basically there are other factors here that will affect the success rate. And they didn't elaborate on this, they just reference another paper there. So
the problem is that
I'm not very sure.
Because for AC part, and if we would like to AC to be large, right? Basically, the larger AC, the better. Right? If AC is smaller to red.
No, larger means is more neutral.
Oh yeah, the larger the neutral. Suppose AC is equal to 0, it means very round. So yeah, so here's the part. So I'm saying that both monotonic and the neutral are smooth, so they can smooth in a very different way. So this is if the landscape is monotonic, that means this SBST can work. But if the landscape is neutral, it does not work. So AC will definitely is not decisive for a successful ratio. And for ICs, it means that it contains more information. That means more sensitive. So it somehow means sensitive. So it somehow it shows that the more sensitive the landscape to the notation, the more likely the more likely SBST can be successful, and vice versa. So that is just the basic idea we have.
Yeah. So from this figure, you can deduce that generally neutrality is harmful for search performance, but ruggedness does not decrease search performance.
But I think AC is not just evaluating the ruggedness, it actually evaluating the smoothness. All right. Okay.
Yeah. So yeah, this will answer the second question. And then now the third question is we try to find the underlying properties of the source code that cause these fitness landscapes. So to do so, we can compare the success rate of the search algorithm and the random walks. And then we can distinguish branches that are trivially covered, impossible to cover, or able to cover with some search effort. And then we can compare the different branch types with their landscape and the source code properties. So this figure is basically for each branch, we check their success rate for random walk and the search algorithm.
Covered by search and covered by random walk. Okay, so I see. So if it's covered by random walk, so it is quite trivial, right?
Yeah. So the branches at the top right are basically means that they can be covered by both search and random walk easily. And then the bottom left means that they can't be covered. And so a large number of branches are at the top left, which means that they are covered well by the search algorithm, but not covered by the random walk, which makes sense. And
so
then,
what kind I'm just curious, what kind of the top left, top right, just so what kind of branch which makes most are hard to cover, but makes random cover easily?
yeah, I mean the bottom right.
I mean the the bottom right.
So this one is there are a few cases that like what you said, they can be covered by random walk but not by the NUS. So this one they will cover that later. Yeah, so now we can partition the branches into these 4 different groups.
Do they provide
Okay,
examples? Do they provide examples on group 4?
Not like concrete examples, but they explain how it looks like.
Okay.
Yeah. So one way so now we can like group them into these 4 different groups, and then we calculate the average values of the different measures. So you can see that neutrality increases from easy to the search group to the hard group.
Let me see.
Which
so that means decrease, right? So this is increase. The easy one. So the higher the smooth. So it means that the random approach is more have better performance when on the neutral it have better performance on the neutral landscape.
Yeah, correct.
That's for easy, but
so,
the random walk also have good performance on the easy branch. So the easy branch, how does the easy these kind of values, what kind of information can those easy values bring us? So it's almost monotonic, or not?
Sorry, what?
I somehow this is becomes bigger, the bigger the neutral, and this is
easy means it's more rugged.
from easy to search to hard. Okay, but the random walk not necessary, but there is the easy branch search very hard. Okay, so please go on.
So for the random walk is the landscape is somewhere in between. So it's likely because of reasons unrelated to fitness landscapes, which we'll go through a bit later. So this figure, basically you want to check if the methods containing the branches were even executed in the first place. So because if the method is not called, then the fitness landscape for that branch will just be, by default, it will just be a plateau. So from this graph, you can see that like the harder branches have lesser number of method executions.
Okay, this is still in line our examination, and there's a test case legitimization. That is so that is we would like to maximize the we would like to maximize the chance of let us untitled method to be executed, right? So I think here we have already got method container branch. Okay, so here this takeaway is that some of the neutral branch is not executed after all.
Yeah.
Okay.
So, but this one, when you're talking about the method not being called, they are talking more about the accessibility. Yeah.
Previous slides. So why it evaluates the number of executions? It should look into the ratio of execution, right? Because for the random walk, when the random walk outperforms the search space, the random walk outperform the search-based approach in very few methods. So given this case, it will definitely will have a small number of executed methods. So it does not mean anything. So somehow we would like to look into harder. The ratio of the methods is more reasonable for us to check, right?
Yeah. So yeah, I'm also not sure why they use like the absolute number. Yeah, but in the next slide they try and find a ratio of the different accessibilities of the different methods. So you can see like for the hard group, like most of the methods are private methods which they cannot invoke or access.
In the US way, it allows us to access some private methods.
Sorry?
I think US rate may allow, because US rate actually allow the test case to use some private methods, if I remember. So at least the US will allow us to access protected method. It allows us to do it because US will have a security manager to control the access security, the access security of the message. So somehow it just feels a bit weird. Complete, please go on.
So this shows that like accessibility is also a primary factor for the fitness landscape. And if you can get some
the takeaway is that some branch is not executed, or the landscape of a certain branch is so neutral, is because they are simply cannot be executed. So the previous slides, both the previous and these slides, means that the previous slide is that it not be executed. The second slide is that they cannot be executed because of their accessibility, the limitation of the accessibility.
Yep. Correct. So secondly, we also want to check like.
Let me see. There's one for inter-procedure distance information. Okay. Yeah, so this actually refers to our ESTA paper. So we are looking to the. Okay, please go on.
So the second thing I want to check is the number of exceptions thrown. So you can see that over here they use like absolute numbers also. But the hard branches are more likely to result in exceptions. And it is possibly due to difficult object construction, and because of some implicit preconditions of a function or a branch, then it's difficult to configure a complex object into a valid one. And the fitness function does not provide any guidance for this.
So the depending on complex object. Okay. So I think that is still the problem we are going tying on.
Yeah. So yeah, you can see what eBook object is trying to do. So improve by considering the code underlying these dependencies.
Okay.
And then thirdly, we also want to check the different condition or branch types. So now we want to find the number of discrete fitness values. So if there are a high number of discrete fitness values, it means that there is like many gradients, or like one smooth gradient to lead to the global optimum. So this will lead to many variants in the fitness values. So this number of fitness values will increase. And yeah, this figure should explain why the search branches do well, because they have
But for
this
hard,
grade.
they still the hard have lower, but it seems that I still have an every for hard branch, they still have over 200 fitness values.
Mm.
For
Yeah,
each branch. So it's supposed to be a higher number. But I think there's more like they start on the local optima. So they're gonna search, and then they move. Then they stuck on Plato. Okay.
Yeah, so they try to account for the high number in the random walk group. So
yeah, they're almost the same, right? On average, they're almost the same.
Yeah. So they hypothesize that these branches require the difficult object construction, which I mentioned previously. And then because search, like a search algorithm tries to minimize the test cases as the secondary goal or criteria, but the random walk, you just invoke manual methods on individual objects. So it doesn't try to minimize the test case or what. So they're saying that because of this, the random walk will have a higher chance to accidentally produce a valid object configuration to pass these test cases. Yeah.
Okay.
For the easy group, it's a lower number because most likely these branches are not embedded within complex conditional code constructs, which means that the ruggedness is likely not the result of gradients, but it's due to frequent flipping if conditions, which is like what you mentioned.
But the problem is that for I think another explanation from me is that for either branch this may just their trivial branch. So maybe they have a seed heuristics for either suite. For either suite, it will actually pick up the values from the constant pool for both static and dynamic constant pool. Aaron, are you familiar with constant pool mechanisms in JVM?
Not really.
So the idea is that the EVS would have a trick. So the EVS would actually, the random methods in EVS would are not necessarily the pure random methods, because it will select the constant of int type, the constant of string type from the constant pool. And a static constant pool are just collected from the constant in your source code. For example, in your source code, you are comparing a string variable with a string array. So if we would like to evolve the test case with a string array, then it will be very hard to do this. But as long as we can randomly construct a pool which pick up the string constant used in the source code, so it will give us a higher chance to randomly pick the string array instead of generating a string array. That makes things easier. So in this case, if they apply these heuristics, if they apply these heuristics, so those branch becomes easier, and it does not require many fitness value. So they can, and actually, if the chance is good, they can just cover the branch within 1 or 2 iterations. In this case, it actually will not generate a lot of fitness values, and it will still have a very high coverage.
Yeah.
So I think easy methods, as long as they adopt some seed and heuristics on that part, we can totally ignore the easy group, because the easy group, just to pick up some randoms, and since they're easy groups, so the landscape does not matter to them. They will still have a large. They will still. I think there are a large number of easy branch, right? How many easy branch are there?
I don't think they mentioned.
Can we show the scatter the plot before? Yeah, you can see. Okay, the easy branch is not as good as is not as many as the curved branch, but I think the easy branch is equivalent to the hard branch. Okay, please go on.
Yeah, so they hypothesize that also these conditions are like easy reference or null comparisons, which are easy to fulfill. So this last figure, they are trying to classify the like 4 different branch types. So for example, most of them consist of integer 0 branches, which represents, for example, an if x where x is a Boolean variable. So this is the so this integer 0 these integer 0 branches cover most of the branches. And then
so you mean that the flat effect is very prevalent among the branch?
yeah. And then for the search group, it contains slightly more integer branches. For example, x more than 10.
Oh, I see. The integer 0 is a flat method, and the integer. So here I see. Let me see. So what does the reference? So this is input and this is output, right? So this is the method or the branch. What does this integer and this 0 means?
I think it's saying like the output.
The output. The output of the branch or the output of fairness.
The branch.
The branch and how does the integer? So let me think. Is that means the integer? So integer and why there's no float or double variable type? And how does this integer, and this should be a dash, right? Oh no, this should be dot. So how does this integer 0 branch is defined? Why is called integer 0?
I'm not very sure. So.
Okay, so please go on. Maybe somehow I can just extract something from your examples, but I just more curious about its definition.
Yeah.
Okay, please go on.
Yeah, this definition we got it from another paper also. So yeah, I'm not very sure about this. And then for the easy group, this part is a bit weird because they say it contains mostly reference null or reference branches, but then if you add them up, it's only 25%. So yeah, not sure what they are trying to claim here. But basically, it's saying that like branches such as x equals to null is quite easy to fulfill. And then for the random walk group, it contains only integer 0 branches, which satisfy their hypothesis that says that the branches are mostly complex objects. So it's hard to produce them.
Huh? It's only if conditions that cure problems are difficult to produce. So can you further elaborate this sentence? What do you mean by can you raise an example where if conditions curate the properties of complicated objects?
So you're saying as something like example like students dot height equals to 100. So like the properties is this up. And then because the complex objects is the student.
And this is more like so what kind of branch type it is?
Sorry?
What kind of branch type it is? Because I just infer from here. So for this branch, given here integer 0, it somehow means that these if conditions is only one operand comparison. So it is just compare operation, compare whether integers with zeros. And an integer, that means this branch compared to this branch compared to two values, and both values are of the integer type. And the reference now means that this comparison are comparing two objects. And given that there will be a special an object is non-object, so it compare the branch compare non and reference and non and reference. And so here comes the questions. Obviously, this branch involves an object. However, the actual variable type it compare are integer. This is the example you raised. So my question is, what branch type does what type of this branch it is?
Yeah. As in you're saying is integer 0, then it's probably doesn't have this. So it's just like just one variable, which is integer 0. Yeah. So the thing is like the branch is easy to fulfill, but it's hard to construct this complex object. Yeah.
Okay, that's good.
Yeah.
So let me see, the hard is 20% of integer. So this part, integer 0 will be considered one almost one. Okay, please go on.
Yeah, so from this we can see that we can improve by considering the Boolean flags. So yeah, that's it for the research questions. Yeah, so to conclude, we try to observe the different landscapes for different types of branches, and we found out that the fitness landscape is highly dominated by neutral areas, and that ruggedness does not seem to be detrimental to the search. So the three main causes for neutrality, as mentioned, is the accessibility of methods, the satisfying the preconditions of methods, and the Boolean flag problem. And then we can improve SBST by adding some interprocedural distance information, or also like using testability transformations.
Yeah, actually, Gordon Fraser is our collaborator. We have approach to address. So that is the Han's work. When the Han work with us, we propose approach about interprocedural distance information. I think Aaron, you have made an excellent presentation here. Very good work, thanks. And here, because this is empirical studies, we definitely would like to share some information or have some takeaways from the results of these empirical studies. So here, I think one of the problems of this approach at this point, I also claim that the ruggedness does not seem to be detrimental to the research. So I have a question of his evaluation of the ruggedness, right? So somehow it depends on, so when it's you apply random work. So the search space could like this. So giving a point, if it's a search in this way, so it will have some ruggedness, but it's search in this way. this this landscape is very smooth, right? Suppose given the random walk, when it combines all the landscape, it combines the landscape of all the space, then definitely it will calculate a high ruggedness because of this portion, right? Because of this portion. But that may not necessarily mean the ruggedness is not detrimental. So giving my examples, suppose this x is equals y and x greater than 1,000. Suppose there's two branch distance. The traditional search-based testing approach will definitely know how to handle this. Easiest way can address these ones, but it will based on some specific seeding strategy or seeding heuristic to address these ones. So this is one of my comments or concerns about this conclusion. But actually, that does not affect. This is a good and well-studied paper. And another comment I will have on this work is that we already are proposing, for example, our examinations. We are already addressing this one. It's more like the precondition of the methods. So we are actually to do the test case legitimizations. We generate the graph, we calculate the graph and generate the test case, and we're all targeting for those empirical the problems reported from these empirical studies. But the good thing for this study that is we do not need to do the empirical study ourselves to check whether the problem we're addressing is popular, whether the problem we're addressing is popular. We do not need to care about this part. So it leaves us a few research opportunity here. And one of the opportunities is that we can rerun the experiment of this interprocedure distant information. So they have two problems here. The problem is that when we find the idea of for us addressing, so basically there's two kinds of work, the same kind of work. So the classical Boolean flat problems can be addressed by the interprocedure disinformation. That is fine. However, there's still a few challenges here. The first is that how do we really address the interprocedure flat problem? So the interprocedure flat problem is like this. Is okay. Suppose this is okay as a method. So we are going to, the idea is that we're going to, so for the search-based testing, so this flag is always there, there's always neutral. The landscape of this flag is always neutral. So even if it is neutral, the way is that we're going to aggregate the branch distance inside this method call so that we can replace the original flat landscape with some smooth or with some monotonic landscape. So, but for now, I think there's a few methods we have a few problems haven't addressed well. And the second is that we have discussed before. So sometimes the traditional SBST are looking into the classic Boolean flag if problems, but sometimes even if the branch is compared integer, even if the branch is an integer branch of integer branch type, but it still have the flag problem. It still have flag effect. For example, suppose there's a method if, suppose there's a method if, return if, suppose this is suppose we return whether it's okay, return 2, right? So if we just using some static protocol analysis, we find this not a flag, it's not a flag method. However, if this okay is look like this, if what it returns 2, and if what it returns 0, that means giving method, it will only return binary value, either 0 and 2. In this case, it is still a flag effect. So here, I think we used to writing some entropy-based idea. So just very similar to what Gordon Fraser's team is doing. For now, I think we do not need to do the entropy here. So because it takes a very long time, one of the ideas is that we can come up with some heuristic to think about the potential flag problems. For example, we conduct the static program analysis. we can have some static program analysis, maybe some template-based or rule-based idea to find those flag effects beyond flag problem. Let me say it again. So we are going to look for the method which is beyond Boolean flag problems, but it still have a flag effect. So I think we can later start with some state analysis to using some template like this. We're going to go through all the methods to see the number. We are going to see the number, whether the return value, even if the return string, even if the return integer, we're going to look into whether we're going to look whether they will return a limited number value. As long as these methods return a limited number value and it is called and used in some branch conditions. In this case, we think it has a flag effect, and we're going to extend our ESTA work into a journal paper and addressing these problems. I think that will be easier for us to get this paper published. Okay.
Yep.
Okay. Aaron, maybe we can talk about more details, especially for when you're debugging in the Swift framework.
Yeah.
And also for this extension, definitely because the ESTA work. So we have work address this problem, and we will have ESTA work, even Gordon Fraser, that is the second author in this paper, in the paper you presented, is our co-author. He's the third author then. In that case, we can somehow further invite him to our another work, and if we have some findings to share, and I will send an email to him and organize your meetings if possible. Yeah. Okay. Thanks a lot for Aaron's presentation again, and I guess all the students do not have the other questions. If not,